Welcome to this solution walkthrough for LeetCode problem number 2015, count number of wonderful substrings.
In this video, we'll explore the problem, break it down step by step, and implement an efficient solution.
Let's dive in.
In this problem, you are given a string called word, which is made up of lowercase English letters. A substring of this string is considered wonderful if it contains at most one character that appears an odd number of times. For instance, in the substring ccjjc, the frequency of each character is either odd or even, so it qualifies as wonderful. However, in ABC, there are multiple characters with odd frequencies, so it does not qualify. The goal of this problem is to calculate the total number of wonderful substrings present in the given string. You'll need to work within the constraints of the input, where the length of the string can go up to 100,000 characters, and you should return this count as an integer.
To better understand the concept, let's look at an example. Suppose the input string is ABA.
The output for this case will be 4 because there are 4 wonderful substrings, A, where A has an odd frequency, B, where B has an odd frequency, another A, where A is counted again with an odd frequency, and finally, ABA, where A has an even frequency and B has an odd frequency.
Each of these substrings satisfies the condition of having at most one character with an odd frequency. Now, consider the input string AB. For the string AB, the output is 9.
Here's why: the substrings A, B, and B each contain only one character, so they are automatically wonderful, giving us 4 substrings.
Then, the substrings AA and BB are wonderful because all their characters have even frequencies, adding 2 more.
The substring AB is also wonderful since all characters in it have even frequencies, contributing 1 more.
Finally, the substrings AB and BA are wonderful because they each have only one character with an odd frequency.
This gives us a total of 9 wonderful substrings. Now, consider a simpler example with the input string he.
For the string he, the output is 2.
The wonderful substrings here are H, where H has an odd frequency, and E, where E has an odd frequency. This example highlights the basic case where each character of the string forms its own wonderful substring. As we wrap up the problem statement, keep in mind the constraints. The string length can go up to 100,000, so any solution must be efficient. Also, remember that substrings must be contiguous, and edge cases like strings with a single character or repeated characters should be carefully considered when designing your solution.
To solve the problem of counting wonderful substrings, we first need to understand what qualifies a substring as wonderful.
Specifically, a substring is considered wonderful if at most one character in the substring has an odd frequency. One intuitive way to approach this is through a brute force method. In this approach, we generate all possible substrings of the given string and check whether each substring meets the criteria. To do this, we iterate over every possible starting index for the substrings and, for each starting point, iterate through all possible ending indices. For each substring, we compute the frequency of each character and verify the condition whether at most one character has an odd count.
While this method is straightforward and easy to understand, it is computationally expensive.
Generating all substrings takes quadratic time, and calculating character frequencies for each substring adds another layer of complexity. This results in an overall time complexity of O(n cubed), which makes the approach impractical for larger inputs. The brute force approach, though simple, is not suitable for large inputs due to its high time complexity.
To address this, we consider an optimized solution that combines bit masking and prefix sums to track character frequencies efficiently.
The core idea here is to represent the frequency of characters in a substring using a bit mask.
In this representation, each bit corresponds to the odd or even parity of a character's frequency, essentially whether a character's count is odd or even.
Using this bit mask, we can track the state of character frequencies for any substring. A substring is wonderful if its prefix mask satisfies one of 2 conditions: either all bits in the mask are 0, meaning no characters have odd frequencies, or at most one bit is set to 1, meaning only one character has an odd frequency. By using prefix masks, we can efficiently calculate how many times each bit mask has occurred as we traverse the string. This allows us to determine the count of wonderful substrings in linear time, reducing the complexity drastically to O(n).
To implement the optimized approach, we follow these steps.
First, we initialize a hash map called prefix count to store the frequency of each prefix mask. We start by setting prefix count 0 equals 1, representing the initial state where no characters have been processed yet.
Then, as we traverse the string, we maintain a variable called currentMask that is updated for each character based on its odd or even frequency.
For each new currentMask, we calculate two things: the total number of substrings with no odd frequencies by referencing prefix count, currentMask, and the count of substrings with exactly one odd frequency. To find these, we flip each bit in the currentMask one at a time and check the corresponding entries in prefix count.
After these calculations, we update prefix count to include the new currentMask. This ensures that as we process the string, we are continually tracking the frequency of all possible prefix masks.
The bit mask operations, like XOR and hash map lookups, are constant time, making this approach highly efficient with an overall complexity of O(n). This efficiency, coupled with a clear and systematic calculation process, makes the method robust and scalable. When comparing these two approaches, the brute force method stands out for its simplicity but falls short in practicality due to its O(n)³ time complexity, making it infeasible for larger inputs. On the other hand, the optimized approach using bit masking and prefix sums provides a significant performance boost, reducing the time complexity to O(n). While this optimized strategy requires more advanced techniques like bit masking and prefix tracking, the payoff in terms of efficiency is substantial.
Considering the constraints of the problem, we chose the bit masking and prefix frequency approach as our final solution.
This method leverages the parity property of character frequencies effectively and avoids redundant computations, making it the best choice for competitive programming scenarios. Though the implementation is more complex, the linear time complexity ensures scalability and makes it the optimal strategy for solving this problem.
The problem we're tackling is to count the number of wonderful substrings in a given string.
A substring is considered wonderful if at most one character in it has an odd frequency. To simplify this, we leverage the concept of bit masks.
A bit mask is a compact way to track whether each character from A to J has an odd or even frequency.
For example, a bit mask of 00000000001 means only A has an odd frequency, while all other characters have even frequencies. The key idea is that a substring is wonderful if either all bits in the bit mask are 0, indicating no odd frequencies, or exactly one bit is set to 1, meaning only one character has an odd frequency. To efficiently identify these substrings, we use the prefix sum technique with bit masks, which allows us to track cumulative character frequencies as we traverse the string, enabling quick comparisons to find wonderful substrings.
To optimize the computation further, we pre-compute all possible single-bit changes to the bit mask. This helps us efficiently check for cases where exactly one character has an odd frequency. The algorithm itself begins with initialization. We use a hash map called prefix_count to store the frequency of each prefix bit mask, starting with prefix_count 0 equals 1 since an empty prefix has a bit mask of 0. We also initialize current_mask to 0, which will represent the cumulative bit mask as we process the string, and a counter wonderful_count to store the total count of wonderful substrings. As we traverse the string, we update the current_mask by flipping the bit corresponding to each character. Then, we check how many times this bit mask has appeared before in prefix_count and add that count to wonderful_count. This step accounts for substrings where all characters have even frequencies.
Additionally, for each character, we check all possible single-bit changes to current_mask. If the resulting bit mask exists in prefix_count, we add its count to wonderful_count, covering cases where exactly one character has an odd frequency.
Finally, we update prefix_count to include the new value of current_mask.
At the end of the traversal, the algorithm simply returns wonderful_count as the total number of wonderful substrings. The data structures involved include a hash map, prefix_count, which maps bit masks to their frequencies, allowing us to perform constant-time lookups and updates for each prefix bit mask. We also use a 10-bit integer, current_mask, to represent the odd or even parity of character frequencies for A to J. The algorithm's time complexity is O(n), where n is the length of the string. This is because we perform a single traversal, and for each character, we perform 10 constant-time checks for single-bit changes, leading to a total of O(n*10), which simplifies to O(n). The space complexity is O1 additional space, as the hash map size is fixed at 2 to the power of 10 equals 1024 unique bitmasks, regardless of the input size. The algorithm is designed to handle a variety of edge cases. For an empty string, the result is 0 since there are no substrings. For a single character, the result is always 1 because a single character substring is inherently wonderful. If all characters in the string are identical, every substring is wonderful since there are no odd frequencies. For strings with mixed frequencies, the algorithm efficiently identifies wonderful substrings using the bitmask technique.
Let's break this down with an example. Suppose the input is word equals ab. We start by initializing prefix underscore count to 0, 1, current underscore mask to 0, and wonderful underscore count to 0. As we process each character in the string, we update the bitmask and count wonderful substrings accordingly. First, we process the character a.
The bitmask flips the bit corresponding to a, resulting in 00000000001.
We check prefix underscore count for this bitmask, finding no matches, so wonderful underscore count remains unchanged.
We then check all single bit changes, again finding no matches.
Finally, we update prefix underscore count to include the new bitmask. Next, we process another a.
The bitmask flips back to 00000000000. This time, prefix underscore count 00000000000 already exists with a count of 1, so we add 1 to wonderful underscore count, making it 1.
No single bit changes match, so we update prefix underscore count.
Moving to the character B, the bitmask flips to 00000000010.
Again, we find no matches in prefix underscore count or for single bit changes, so wonderful underscore count remains unchanged. We update prefix underscore count.
Finally, processing another B, the bitmask flips back to 00000000000, and prefix underscore count 00000000000 now has a count of 2.
Adding this to wonderful underscore count gives us a total of 3. After updating prefix underscore count one last time, the traversal is complete.
The final result is wonderful underscore count equals 3, meaning there are 3 wonderful substrings in the input string. This step-by-step example demonstrates how the algorithm efficiently counts wonderful substrings by leveraging bitmasks, prefix sums, and hash map lookups. The approach handles character frequencies systematically and avoids the inefficiencies of a brute force solution, making it both elegant and optimal for real-world inputs.
To solve the problem of counting wonderful substrings, we start by importing defaultdict from the collections module. This allows us to manage the frequency of bitmasks efficiently.
The solution class contains the method wonderful substrings, which takes a string word as input. Inside, we initialize a prefix underscore count dictionary using defaultdict, int, which will keep track of how many times each bitmask has been seen so far. Initially, we set prefix underscore count 0 to 1 because an empty prefix corresponds to a bitmask of 0. Next, we define 2 variables, current underscore mask, which tracks the ongoing bitmask as we process the string, and result, which accumulates the total count of wonderful substrings.
The core logic involves iterating over each character in the input string. For each character, we update the current underscore mask by toggling the bit corresponding to the character. This is achieved using the XOR operation, where we shift 1 left by the difference between the ASCII value of the character and that of a. After updating the bit mask, we add the count of the current underscore mask from prefix underscore count to our result, since this represents the number of valid substrings ending at the current character with an even frequency for all characters. Additionally, we need to account for substrings where at most one character has an odd frequency. To handle this, we iterate over all 10 possible bits, representing the letters A to J, and calculate the result for masks that differ from the current bitmask by exactly 1 bit. This is done by XORing current underscore mask with 1 shifted left by I. For each of these toggled bitmasks, we add the corresponding count from prefix underscore count to the result. Finally, we update the prefix underscore count dictionary with the current bitmask by incrementing its count, ensuring that it reflects the current state for future iterations. After processing all characters in the string, we return the result, which now contains the total count of wonderful substrings. Here, we begin the Java implementation for counting the number of wonderful substrings. First, we import the necessary classes, including hashmap and map, which will help us store the frequency of prefix bitmasks. In the solution class, we define the method wonderful substrings that takes a string word as input. To efficiently track the frequency of bitmasks, we initialize a map called prefix count. This map will store the count of each prefix bitmask we've encountered. We also pre-populate it with a key value pair of 0 and 1, representing an empty prefix. Next, we declare two variables, current mask, which will hold the current bitmask as we process each character, and result, which will store the total count of wonderful substrings. Then, we loop through each character in the input string using a for loop. Inside the loop, we update the current mask by toggling the bit corresponding to the character's position in the alphabet. This is done using the XOR operator and bitwise shifting. After updating the mask, we check how many times this specific bit mask has already been encountered and add that value to the result. Additionally, we account for scenarios where the bit mask differs by exactly 1 bit, as this allows us to include substrings with at most 1 odd frequency. To achieve this, we iterate through all possible bit positions from 0 to 9, toggling each bit in the current mask and checking its frequency in the map. The counts for these adjusted masks are added to the result as well. After processing all the adjusted masks, we update the prefix count map with the current bit mask. This is done by incrementing its count in the map, or initializing it to 1 if it hasn't been encountered before. This ensures that the map stays up to date as we continue processing the string. Once the loop completes, the result variable will hold the total number of wonderful substrings. Finally, we return this result as the output of the method. This implementation efficiently computes the desired result by leveraging bit manipulation and a prefix frequency map, allowing us to handle the problem in linear time relative to the size of the input string. To solve this problem, we start by initializing 3 key variables. First, prefix underscore count is a dictionary that tracks how often each bitmask appears, beginning with 0, 1, to account for the initial state where no characters have been processed. Next, current underscore mask is set to 0, representing the XOR of character bitmasks encountered so far. Finally, result is initialized to 0, which will store the total count of wonderful substrings. In the first iteration, we process the character A. The bitmask for A is calculated as 1, ord A, which updates current underscore mask to 1. Since this mask doesn't exist in prefix underscore count, the result remains unchanged at 0. We also check masks that differ from current underscore mask by 1 bit, but none of those masks exist in prefix underscore count either. Finally, we update prefix underscore count to include the current mask, setting prefix underscore count 1 equals 1. In the second iteration, we encounter another A. The bit mask for A toggles the corresponding bit in current underscore mask, resetting it to 0. Now, when we add the frequency of current underscore mask from prefix underscore count, we find it occurs once, so result is updated to 1. Checking masks that differ by 1 bit reveals no matches in prefix underscore count. We then increment the count of current underscore mask in prefix underscore count, setting prefix underscore count 0 equals 2. Moving to the third iteration, we process the character B. The bitmask for B updates current underscore mask to 2, and since this mask doesn't exist in prefix underscore count, the result remains at 1. However, when checking masks that differ by 1 bit from current underscore mask, we find that the mask 00000000000 exists twice in prefix underscore count. Adding these two occurrences to result gives a new total of 3. Finally, we update prefix underscore count with the current mask, setting prefix underscore count 2 equals 1. In the fourth iteration, we handle another B. The bitmask for B again toggles the corresponding bit in current underscore mask, resetting it to 0. Adding the frequency of current underscore mask from prefix underscore count, which now equals 2, increases result to 5. When we check masks differing by 1 bit from current underscore mask, we find 2 matches, 00000000001 and 00000000010, each appearing once in prefix underscore count. Adding these counts increases result to 7. Finally, we update prefix underscore count to reflect the new count for current underscore mask, setting prefix underscore count 0 equals 3. With no more characters left to process, the final output for this example is result equals 7. Now, let's look at another example with the word ABC. We begin with the same initial setup, prefix underscore count starts as 0, 1, current underscore mask is 0, and result is 0. In the first iteration, we process the character A. The bit mask for A updates current underscore mask to 1. Since no matching masks exist in prefix underscore count, the result remains unchanged. We then update prefix underscore count to include the current mask, setting prefix underscore count 1 equals 1. In the second iteration, we process B. The bit mask for B updates current underscore mask to 3. Checking for masks differing by 1 bit reveals that 00000000001 exists once in prefix underscore count. Adding this count updates result to 1. Finally, we update prefix underscore count to include the current mask, setting prefix underscore count 3 equals 1. In the third and final iteration for this example, we process the character C. The bit mask for C updates current underscore mask to 7. Checking for masks differing by 1 bit reveals that 00000000011 exists once in prefix underscore count. Adding this count updates result to 2. We then update prefix underscore count to include the current mask, setting prefix underscore count 7 equals 1. With no more characters to process, the final output for this example is result equals 2. Now, consider the third example with the word ZZZ. As before, we initialize prefix underscore count as 0, 1, current underscore mask as 0, and result is 0. In the first iteration, we process Z. The bit mask for Z updates current underscore mask to 33554432, a binary representation where only the 26th bit is set. Since no matching masks exist in prefix underscore count, the result remains unchanged. We then update prefix underscore count to include the current mask, setting prefix underscore count 33554432 equals 1. The optimized solution, on the other hand, avoids the inefficiencies of the brute force method by counting special subsequences dynamically, without generating them explicitly. It uses 3 variables, count underscore 0, count underscore 1, and count underscore 2, to track the counts of subsequences ending in 0, 1, and 2, respectively. This reduces the time complexity to O(n), because each element in nums is processed in constant time, and the loop iterates n times. The space complexity is also optimized to O(1), as no additional data structures are used. Now, whether the input contains only zeros, a random mix of zeros, ones, and twos, or even all twos, the algorithm still processes each element once, maintaining a consistent O(n) time complexity. Mathematically, the big O notation is derived directly from the loop's n iterations, multiplied by the constant time operations within each iteration. This ensures that the solution is both time and space efficient, making it much more scalable compared to the brute force approach. When solving this problem, there are some common mistakes that can lead to incorrect results or inefficient solutions. First, a frequent error is misunderstanding the order constraint of 0-1-2. The subsequences must follow this specific order, and counting subsequences that include all 3 numbers but ignore their sequence will produce invalid results. Remember, the order is crucial to the problem's requirements. Another mistake is relying on a brute force approach to generate all possible subsequences and filtering out the valid ones. This is highly inefficient because the time complexity of generating all subsequences is O(2 to the power of n), which is computationally prohibitive for large input sizes, such as n up to 100,000. Lastly, failing to handle large numbers properly is another common pitfall. The problem requires you to apply modulo 10 to the power of 9 plus 7 at every step of calculation. Neglecting this can lead to integer overflow, causing runtime errors or incorrect outputs. Always ensure the modulo operation is applied consistently throughout your solution. Another area where mistakes often occur is confusing subsequences with subarrays. A subsequence does not require the numbers to be contiguous within the array, so treating it like a subarray will lead to incorrect logic and missed edge cases. For example, valid subsequences can skip over elements in the array,
as long as the order of 0-1-2 is preserved. Additionally, many errors stem from not initializing base cases properly in the dynamic programming approach. If the counts for subsequences starting with 0 are not correctly initialized, the solution will fail to count subsequences accurately, especially in cases where the array begins with 1 or 2. Proper initialization ensures that the counting logic accounts for all valid subsequences, even under edge conditions. These mistakes highlight the importance of understanding the problem's requirements and setting up the solution carefully from the start. In interview settings, this problem tests your ability to recognize patterns and design efficient solutions.
One key insight is identifying this as a dynamic programming problem with constraints.
Recognizing the need to maintain state variables for counting subsequences ending in 0, 1, and 2 is essential for solving it efficiently. Highlight the optimal substructure of the problem, where the state transition for each number builds on the counts from previous states. For example, when encountering A1, the count of subsequences ending in 1 should increase based on the count of those ending in 0. It's also important to discuss edge cases during an interview. For instance, what happens if the array has no 0s, 1s, or 2s, or if it contains only identical numbers? These scenarios often come up in interviews. Finally, presenting a clear complexity analysis is crucial. Explain how the optimized dynamic programming approach achieves O(n) time complexity with O(1) space, which is critical for handling large input sizes. To deepen your understanding of this problem, you can explore related problems that build on similar concepts. For example, LeetCode 491 focuses on finding increasing subsequences but without the specific constraints of 0-1-2. Another is LeetCode 673, which deals with counting the number of longest increasing subsequences, introducing a different flavor of dynamic programming. LeetCode 940 emphasizes counting distinct subsequences with constraints, which tests your ability to manage unique combinations efficiently. Lastly, LeetCode 300, the longest increasing subsequence, provides a foundational understanding of subsequence-related problems and is a great starting point for beginners. In terms of alternative approaches, the dynamic programming technique remains the most efficient. By using 3 variables, count_0, count_1, and count_2, you can track subsequences ending in 0, 1, and 2, updating them as you iterate through the array. While this method requires meticulous handling of modulo operations, it achieves the optimal time complexity of O(n) and space complexity of O(1), making it the best choice for large inputs. Finally, let's briefly consider 2 other approaches, although they are less practical. The first is recursive backtracking, where you recursively generate subsequences and count the valid ones. While this method provides a clear, conceptual understanding of the problem, it is extremely inefficient, with a time complexity of O(2 to the power of n). This makes it unsuitable for large inputs, though it can be helpful for educational purposes or when working with very small arrays. The second is naive brute force, which involves generating all possible subsequences and filtering for valid ones based on the 0-1-2 order constraint. Like backtracking, this approach is also impractical due to its exponential time complexity. While these alternatives can provide insights into the problem, they are not viable solutions for competitive programming or real-world input sizes. Instead, focus on optimized dynamic programming for efficiency and scalability. Great job making it to the end. To summarize, we used a dynamic programming approach to solve the problem efficiently, focusing on time and space optimization. Remember to apply these techniques to similar sequence-based problems. Thanks for watching, and don't forget to like, subscribe, and share this video for more helpful content. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!